Hello friends, imagine you need to print a full multiplication table. Every row, every column, all the products filled in automatically. You could write one line of code per cell, but that would take forever and fall apart the moment the table size changes. What you really need is a way to repeat work inside work. A loop that itself lives inside another loop. That is exactly what nested loops do. They let you move through 2 dimensions at once. Rows and columns, layers and items, grids and matrices. By the end of this video, you will understand how nested loops work, how to read them step by step, and when to reach for them with confidence. Let us start with the foundation you already know, a single loop. Alright, before we nest anything, let us make sure the single loop mental model is solid. A for loop has 3 parts, a starting value, a condition that keeps it running, and a step that advances it. In code, you write for, then I equals 0, then I is less than 5, then I increment. Each time the condition holds, the body runs once, then I advances, and the condition is checked again. For 5 iterations, I takes the values 0, 1, 2, 3, 4, one dimension of movement. Think of it as walking along a single row of cells, left to right, hitting each one exactly once. That one-dimensional rhythm is the building block. Now watch what happens when we place that exact same idea inside another loop and let it repeat. That is where things get interesting. Now let me show you what nesting actually looks like. We have an outer loop. I goes from 1 to 3. Inside its curly braces, before anything else can happen, lives a complete second loop. J also goes from 1 to 3. The rule is simple. The inner loop must run all the way through before the outer loop takes a single step forward. So when I equals 1, J runs 1, 2, then 3, printing 1, 2, and 3. Then the outer loop advances. I becomes 2, and J resets to 1 and runs all the way through again, printing 2, 4, and 6. Then I becomes 3, and the same thing happens one final time. The outer loop ran 3 times. The inner loop ran 3 times per outer iteration, 9 executions total. The key insight is that I controls which row you are on, and J controls which column. Up next, we will visualize exactly that rhythm on a grid. Here is the interesting part. Picture the output as a grid. The outer loop, I, moves you down the rows. Each new value of I starts a fresh row. The inner loop, J, moves you across the columns. Each new value of J fills in the next cell. When I equals 1, J sweeps across all 3 columns, printing 1, 2, and 3. That fills row 1. Then I becomes 2 and J sweeps again, printing 2, 4, and 6. Row 2 is done. Finally, I becomes 3, and J sweeps one last time. 3, 6, and 9. Fill row 3. The grid is now complete. Every cell is the product of its row index and its column index. This 2-layer rhythm, outer advances once, inner completes fully, repeat, is the heartbeat of every nested loop you will ever write. But there are 2 traps that catch almost every beginner, and we need to look at both of them. Let me show you the 2 mistakes that trip people up most. The first is an off by 1 error. If you write J is less than 3 instead of J is less than or equal to 3, J only reaches 2, your third column never prints. Always double check whether your condition should use less than or equal to, and trace 1 iteration mentally to confirm the last value actually executes. The second pitfall is reusing the same variable name. If both loops declare a variable named I, the inner I shadows the outer one. The outer loop's counter is hidden, and your row logic breaks entirely. The fix is straightforward. Use I for the outer loop, and J for the inner loop. Different loops need different names. These 2 habits, careful boundary checks and distinct variable names, will save you hours of debugging. Now let us wrap everything up. Alright, let us bring it all together. The core rule of nested loops is this. The outer loop advances by 1 step, the inner loop runs completely, and that cycle repeats until the outer loop finishes. That rhythm is what printed our entire multiplication table, row by row. One thing to keep in mind, if both loops run n times, you get n squared total iterations, which we express as big O of n squared. That grows quickly, so nested loops are powerful, but use them deliberately. The classic situations where they shine are matrix and grid traversal, generating multiplication or pattern tables, and comparing every pair of elements in a list. Remember the 2 pitfalls. Check your boundary conditions carefully, and always use distinct variable names for each loop. Thanks for watching, and I will see you in the next one.